So far we have discussed about detection of edges using different techniques and different masks. Now let's take the example of real world problem. Here we have a function fx. Here intensity is the function of x, and if I take the gradient of this function by just doing say a right difference, then what I will do is apply my derivative operator and I'll get this result. So after seeing this plot, one might ask, where is the edge? Like we cannot find the edge in this figure, and we can see that edge in the function. However, the plot of derivative shows only mesh, so it's hard to tell about the edge. So, and the problem of course is that we have added the noise. So, and the noise has caused us to have this positive and negative derivative all over the place. So let's look a little bit more about the effect of noise and some of our derivatives and what we might do about them. Here is an image. Again, this is the image segment of zebra strips, and here we have a gradient image as well. And what we can start to see is that we add noise to the image and the gradient starts to fall apart. Like we can see here, we have the image is corresponding gradient, and we increase the noise and see its corresponding response to the gradient of the image. And here we are starting to see that we had this little bit of Gaussian noise, and now it's turning into this big salt and pepper noise. And it feels like with the salt and pepper noise, these large spikes are happening within the derivative. We can see here large spikes in this derivative or in this gradient image, and so we have to handle that noise somehow. And the question arises, how we will handle this noise? And the answer is easy. We will filter or we smooth the noise to get rid of it. So again, here is a function fx. So now here's a function, and what we do is we smooth this function with this kernel z, and this is the with the sigma 50 we apply a smoothing function, this kernel z, and we are just gonna smooth it. And so we when we smooth it, we get this g convolved with f, and this is the convolution. This is the result after the convolution. Here we convolved g with f, and now we get nice smooth and after we do the differentiation, we get this nice smooth function, and this is our edge, and where we get the nice smooth peak. So here is the edge. We can easily find out the edge. So the edge is going to be at this peak right here, and here we get the peak here. So basically, in order to find our edge, we are going to have to apply smooth gradients. So how? And so somehow, and look the some peaks. And since the differentiation is convolution, here we can see, since differentiation is convolution and convolution is associative, the derivative of g convolved with f is same as the f convolved with the derivative of g. Here we can see here we have got this derivative of f convolved with g is same as f convolved with derivative of g, since we have already stated that this is the differentiation differentiation is convolution and convolution is associative. We have discussed in our previous lectures. So this will save us our operations. So what I do is we'll take the g and take the derivative of g. Here we'll take the derivative of g, and when we apply that function directly to f, and we apply this to f, and we get out the same value that we got last time, and which has to be because of the associative property and linear operations and derivatives and filtering these linear operators. And that also saves the operations because we can just take the filter and apply it, and no more derivative have to be done. Like we can just take this filter, we can take this filter directly and then convolve it with this function. We'll get this peak. So here we have got, and the last question one is we have this nice peak and we have to find maximum of that derivative. Here we have got this nice peak and we have to find the derivative of this. And how do we find the maxima? And we take more derivative. Suppose if we take more derivative, now instead of taking single derivative, we're gonna take second derivative, and before h was just a Gaussian. If we take the derivative of Gaussian, now if we take the second derivative of Gaussian operator, and we get this inverted Mexican hat, we can, like, if we take the second derivative of this Gaussian, we get this this inverted Mexican hat. And now if we convolve this kernel with our function fx, we get this nice zero crossing, like we get this nice zero crossing, and with this here we get the strong slope, and this is what corresponds to our edge and this zero crossing. And in this idea of strong slope zero crossing, we don't have to find the general maxima, and we just have to find any place where the value of 0 and that nearby has a strong gradient. Like we just have to find, if we find this zero crossing point, we don't need to find the maxima, and we obtain this by using the second derivative of Gaussian operator.